We'll proceed in Stokes theorem. We are continuing discussion for the curl in calculus, Stokes theorem, and we'll talk little about curl vector field. Okay, so Stokes theorem. What we have seen till now is if I have a vector field that is algebraic vector, then its line integral along a particular line, that is capital F, that is the vector field dot dr vector, where r vector is the line or curve. What is the integration of vector field capital F along a line from point A to point B? If that is the case, then vector field capital F dot product dot vector product dot dr vector, where r vector is the line, is the curve. If that is the case, then this is called line integral. If vector field is force field, then capital F dot dr vector, the line integral dr vector, this line integral of this vector field will result into work done. Force vector dot dr vector, where r vector is displacement vector or curve vector, both are vector field. In that case, this comes as work done. Force into displacement is work done. So, otherwise, if capital F is simple vector field, then vector field capital F dot dr vector, then this is called line integral, where I have r vector. If I have this as vector field, if I have this as vector field, if I have this as vector field and this is the line, then line integral of this vector field capital F is capital F dot dr vector, where this is r vector, capital F vector dot dr vector, where from point A to point B, if this is a vector field or force field and there is an item that moves from point A to point B because of this vector field capital F, then that is the work done if vector field is force field. Otherwise, this is called line integral. Capital F dot dr vector is also called line integral from point A to point B where it did the displacement. Okay, so this is called kind of line integral. This is equal to, if this point A and point B, if B is also A, means A to A, I mean in a closed loop. If I have a closed loop and then this is a vector field, then there is a point A back to point A, then this is also called that circulate. This is circulation, right? This is circulation. This is circulation. Point A back to point B. The line integral of circulation or integration from A to A. Line integration of a circulation. Line integral of a circulation. A to A or integration at the bottom right C. Okay, if that is the case, then capital F dot dr vector equal to d integration over surface. Now, if there is a circulation, if there is a closed path, then certainly there is a surface. Okay, or okay, should I cut it? Okay, now consider this. So this is also, this is, if I take only the perimeter, then from point A back to point A, back to point A, okay, that line integral of a force or vector field capital F dot dr vector, where r vector is the perimeter, that is x square plus y square equal to a square. Integration from A to A in a circle. If this is force field or vector field is path independent, then certainly A to A integration will be 0. If it is not path independent, then it will produce curl, rotation tendency. If that is the case, then from A to A or in a circular path capital F dot dr vector, this full integration is not 0. If that is the case, then Mr. Green is saying that take this surface, take this surface. If you have a circulation, then whatever comes under this, so you can take this surface, full surface, okay? Then integration over surface, df2 by dx, where capital F is the vector field, then it has component as f1i plus f2j. If that is the case, then integration over a surface, line integrally integration over the circulation line. Now integration over the surface that is under the line. Integration over the surface is df2 by dx minus df1 by dy, and then dA integration with xy plane. Integration with xy plane. Okay, dA integration with xy plane. Okay, so circulation, that is circulation, circu, cir, in, circulation integral in a closed loop, integral in a closed loop, capital F dot dr vector, capital F vector, capital F, on top place one arrow mark, capital F arrow mark dot d, calculus d r vector, from point A to A, or circulation line integral equal to whatever surface is coming under this circulation, integration over that surface, df2 by dx minus df1 by dy, dA, small d, capital A, dA. Okay. Now, if left hand side is scalar, right hand side is also scalar. This is considered that your item it is kept on xy plane, something like this. Okay. Or this is the case. Okay, if it is not kept on the xy plane, then surface is like this. If this curve is moving like this, then slowly we will move to Stokes theorem, same theorem. Whatever Mr. Green is saying, df2 by dx minus df1 by dy, that is curl of vector field capital F. If it is a curl, then it has a direction. df2 by dx minus df1 by dy, this is the curl when the kind of the force field has two components, x and y, means everything is in xy plane. If everything is in xy plane, then df2 by dx minus df1 by dy, that is curl of vector field f, dA, dA means integration with xy plane, integration over the surface, that circulation contains the surface, in a circulation surface. If that is the case, then integration over surface, if it is Cartesian coordinate and if it is a circle, then it will become minus radius. If it is a circle, and this is the center, then minus a. If it is a radius, then minus a to plus a, and y is also minus a to plus a. That is the surface. Integration at the bottom, right, S, capital S, that is the surface. If that is the case, then it will be broken into two in double integration. One is from minus a to a, that is x. Y is again minus a to a, that is y. If it is a rectangle, then you can say 0 to width and again 0 to height, as per your wish. df2 by dx minus df1 by dy, dA, that is xy plane. If I am taking, let's do one example. Okay, consider I have force field as minus yi plus xj, minus yi plus xj. How it looks when on the x-axis y is 0, then xj means the kind of this vector field is perpendicular, right? So this is x-axis and vector field is minus yi plus xj. yi minus yi plus xj. This is origin. So this is x. So on x-axis y is 0. So it will have, so this is the vector field here. On y-axis where x is 0, then vector field is along this direction minus y. So it looks like vector field is a circular, time in a circular it is a tangent. Can you say this? Whatever. If vector field, capital vector field is minus ya plus xj, if that is the vector field, then what is the curl it would generate? Curl is df2 by dx minus df1 by dy. That is the curl. So df2 by dx is 1 minus df1 by dy is minus 1. Minus 1 is 2. So curl factor is 2. Now if I calculate the line integral, capital F dot dr vector integration in a loop, that is same as the loop generates a surface, right? A circular loop, I'm sorry, a closed loop generate a surface. That surface integration with curl dA. So curl is 2 dA. dA is dx dy in Cartesian coordinate. But if I take polar coordinate, that is easy because it is a circle, right, at the end. So then it is r d theta dr. So dA on xy plane for polar coordinate is r d theta dr. Now integration is r is 0 to a, that is the circle, and theta is 0 to 2 pi. Now it is 2 r d theta dr or 2 r dr d theta. R dr becomes r square by 2 and into 2 gone. R square will become a square as per the integration 2 pi. So 2 pi a square is the line integration in a closed loop when vector field is minus yi plus xj. This proves that vector field is not path independent. If it was path independent, then closed loop line integration would have been 0. Okay, so that is the case. So this is not path independent. But so quickly through Green's theorem, we can calculate it. What Mr. Stokes is saying? Mr. Stokes is saying that not necessarily that you think about xy plane only. What is hidden in Green's theorem? This is what Mr. Stokes is saying. What is hidden in Green's theorem is you're talking about xy plane only. So df2 by dx minus df1 by dy, that is the curl, then its direction is k vector, hidden k vector. And you have xy plane, so xy plane, the direction is again k vector. So k vector is missing here. Let's talk about direction. When Green's theorem lands in a field of direction and 3D, not 2D, 3D, then it comes as Stokes' theorem. Stokes' theorem say rather than df2 by dx minus df1 by dy, that is curl of f, just say curl of f, where f vector field is 3D. It can be like, I said minus yi plus xj, it can be like minus y plus z I plus xj plus xyk, whatever, it in 3D. So if your vector field is in 3D, so earlier I was taking x-axis, y-axis. Now take x-axis, y-axis and z-axis. So if it is in 3D, then consider that line integral of any closed region. So this is line integral in any 3D. Line integral in any closed region. Line integral in any closed region. Integration C in any closed region. Line integral in any closed region. Capital F dot dr vector equal to integration over surface. He is also saying integration over the surface. After all, it makes a surface. Integration over the surface and then curl of f, because curl of f is very big. It is like df3 by dx, df3 by dy minus df2 by dz in I direction minus determinant of the matrix. This is what I am trying to calculate. Minus df1 by dz, df1 by dz, df1 by dz minus df3 d df3 d, I mean df3 by dx minus df1 by dz j plus df2 by dx minus df1 by dy k. Means this is the kind of new curl vector. Just say curl of f. So curl of f dot. Now new terms come as dot product. Dot dA vector. Now why a vector is coming into the picture is, consider that, okay, so consider that I have a rectangular region in 3D space. This is in xy plane, but rectangular region in 3D space. This is rectangular region in 3D space. Now this surface can be like this also. Can you see now? I have done this kind of stuff. So kind of molding it, right? So surface become like this. Now whatever the circulation I had earlier, the circulation was perfect. In earlier when we are not talking about the vector in surface. So circulation was for a rectangle. Now we have a rectangle. I'm not saying I don't have rectangle. This is nice rectangle. But Stokes is saying that the circulation, what we are seeing around it, not required that the surface will be flat. Surface can be anything. In that way, still we have circulation. Can you see it? Or if I have rectangular surface, then if I mold it like this, then it, now if I mold it like this, then it has two circulation. Can you see? One circulation on this side and another circulation on this side, but both direction will be different because it belongs to same surface, right? So if this is counterclockwise, then this will be clockwise. He is talking about direction in the circulation. So Green is also saying direction in the circulation. So Mr. Green is saying the direction in the circulation is anti-clockwise. So Stoke is also saying that it should be anti-clockwise. But if it has two circulations, one circulation along this side and another circulation on this side, then if one is anti-clockwise, then one will be clockwise. So that the normal vector, the curl vector, if I calculate for a surface, if I have a vector field, this surface has a normal vector. This surface has a normal vector. If you closely see, we talked about line integral and then same line integral through Green's theorem on a surface that is curl of f dA. If I if I take dA this side, then it is line integral by dA equal to curl of f, more or less. If that is the case, then this is called circulation density. Whatever line integral I have calculated along the line, if it makes a circle, and whatever the area of the circle is, if I divide this line integral by the area, then it becomes circulation density, where circulation density has a vector, because circulation density equal to curl of f. If it is curl of f has a direction. So what is the direction of circulation density? Then it is said that if there is a vector field, if there is a vector field like this, and now I'm talking about 3D, and this is a circle which has this area, line integral is this divided by the area is circulation density. If this is circle, then perpendicular to is the direction of the circulation density. If I keep moving like this, then line integral will change because dr vector is changing. Change to a level where the circulation density will be maximum. Consider here it is maximum. Then this is the surface and this is the normal to it. So this is the circulation density has direction. So there is a theorem also that circulation density of any vector field F, it is written as CIRC, circ, at the bottom right, the type circulation density. Okay, then you write CIRC, I believe N. CIRC at the bottom right, just write small n. Then it becomes circulation of F. It becomes circulation density of vector field F along n direction. So right hand thumb rule comes into the picture. So if circulation density is along this direction, then your curve is like this. The circle is like this. So if circle is counterclockwise, then circulation density is up. Okay. If that is the case, then circulation density of any vector capital F is equal to curl of F dot n. Curl of F, curl of F, curl of F. Circulation density as such is a scalar quantity, but hypothetically we say it is in direction of n vector equal to curl of F dot n vector. Then it becomes now scalar equal to scalar. This is the scenario. But Mr. Stokes is saying that line integral in 3 dimensions of a line integral in 3 directions of a line, where the line or the circulation belongs to a surface. Yes, now emphasis is on surface. Mind it. Okay. Then if I have a rectangular region, and this is the circulation, this is the line around the rectangle. If I'm calculating integral of the force, integral of a vector field along this circulation, then there is a surface integration. This is what Mr. Stokes is saying. Surface integration of the surface, where surface may not be flat. Surface can be like this. Surface integration of a vector field, of curl of the vector field capital F dot dA vector, where A vector, area vector, earlier we had line vector, you remember. Now area vector. So this area vector, now A has area vector, dot area vector. Now area vector, if I take a flat rectangle, then if this flat rectangle is like this, then area vector is like this. But everywhere vector is same, means it's parallel. But if it is if it is not flat, then here area vector is like this, here area vector is like this, here area vector is like this, here area vector is like this. Means area vector is vector field, because it is algebraic. As if I change xy coordinate, this area vector is changing. Means it is dependent upon independent variable x and y. This proves that now we cannot say that line integral along the circulation of a surface. If this is the surface and this is the circulation line, the line integral along the circulation is vector field F dot dr vector equal to surface integration of vector field capital F, curl of vector field capital F dA, because A is changeable. It is not xy plane, it is changeable. Then it comes as full-fledged vector calculus. I mean dot dA vector. So curl of F dot dA vector integration along in a surface is the Stokes theorem. Now what he is saying, that you take any small strip on the surface. If this is the surface, take any small area strip, considering that is flat. If that is flat, then there if you try to calculate the line integral along the boundary of that surface, small, this is very small. Consider this is very small, and this is somewhere on this molded surface. So this is flat. Now if I try to calculate line integral over this, then whatever the circulation I am seeing, that circulation density, what is circulation density? Circulation density, that is line integral divided by the area. If I multiply it by area, then it gives me line integral. So Mr. Stokes is saying, take any dA, small area, consider this is dA. If this is dA, then circulation density divided by dA, circulation density divided by delta A, is nothing circulation density, I'm sorry, circulation density is line integral divided by delta A. If I multiply it by delta A, then it becomes the the line integral. Line integral by delta A is circulation density multiplied by delta A is line integral. Mr. Stokes is saying that whatever your circulation density here is, multiply it by delta A, it will give you the circulation of any small region on a surface. I have taken very small area region that I enlarge and it became like this. It's a flat because it is very small. If that is the case, then circulation density into this area dA is nothing but the line integral over this circulation. This is what Mr. Stokes is saying. So circulation density into delta A. Circulation density is nothing but line integral divided by delta A. Circulation density, once I just now I proved that circulation density is nothing but curl of circulation density of vector field capital F equal to curl of f dot n vector, where n is the direction of the circulation density or surface of the circle when we calculate a circulation density. We talked that circulation density differs if I change the orientation of the circulation. If this is the circulation where it has the surface, if I change the orientation of circulation density changes. Wherever it is maximum, that is the circulation density. So circulation density of vector field F equal to curl of F dot n vector, where n is a unit vector that is for the circulation density. What we have now? So Mr. Stokes is theory that if you take a surface, and you take a small strip here, that small strip is this, then then the circulation of this line integral of this small region is nothing but circulation density of this region into delta A. Circulation density is nothing but curl of F, vector field F is curl of vector field F dot n vector, that is the direction of the circulation density. So curl of F dot n vector, that is direction of the circulation density, unit vector. If n goes, so now what we have? The circulation is nothing but circulation density into delta A, where circulation density is line integral by delta A. That's why if I want to calculate the line integral, that is circulation density into delta A. Circulation density is of F is curl of F dot n vector, because circulation density has a direction and circulation density is a scalar quantity. So curl of F dot n vector, where n vector is the direction of the circulation density. This n vector, unit vector, will go in delta A and it becomes dA vector or delta A vector, whatever it is. Now the line integral of this molded surface, any small region, very small region, that is, if I enlarge it, if that is this, then line integral of this small region is nothing but the curl of vector field F dot delta A vector, because n vector goes inside delta A and it becomes delta A vector, because A has n direction. Now start calculating. Now take all the small pieces, so that line integral will be you are calculating for the full circulation. If you take this all small pieces and add it, then it will become a kind of summation of whatever we calculated. Curl of F dot dA, where delta first delta A, second delta A, third delta A, fourth delta A, fifth delta A vector, where delta A vector keep on changing everywhere. So if I have curl of F dot dA vector, delta A vector, where delta A is delta A, where if I add all the delta A, then it becomes integration. Integration for a surface, full surface, integration for a full surface, curl of F dot dA vector. Someone would ask, If I take a small region, then again adjoining a small region, then adjoining a small region, what about the line that is common to two regions? If I take a small region like this, again I take a small region this, then what about common region that is in two regions? There the curl field will be opposite to each other because of the direction. If both I am taking counterclockwise, then one will be counterclockwise, other will be in clockwise. So they would cancel each other, and at the end I am calculating. It is understandable, right? So if I have taken two small regions like this, and then I am calculating the line integral, and for this counterclockwise here it is going like this because this is common line, and for here it is going in anti-direction. So here line integral will be 0. At the end we are end up in line integral calculating the peripheral one. So if I take big region, if I am taking calculating the kind of uh, uh, the if this is the surface and trying to calculate the circulation of the surface, then all small region intersection will cut out, and finally we'll end up calculating the circulation for the full path. This is what is required. So we prove the Stokes theorem. So Mr. Stokes is saying that circulation density of this 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 surface, where surface is not flat, not circulation density. If surface is not flat, then line integral along the circulation. Now circulation is not a on a same plane. Just whatever you are making to see, whatever you are seeing it, the way it is like this here and there. So in a circle, in a closed loop, the circulation, the line integral for this is nothing but surface integration, surface integration curl of f dot d a vector. This is what where a vector will is vector field. It is variable as per we take x and y and z. Okay, this is what Mr. Stokes is saying. Okay, I'll do small exercise and then later we'll see curl vector. It is too late. So what exercise we have? Consider a vector field like I believe magnetic vector field or whatever it is, its equation capital B. There is a magnetic vector field or any vector field, capital F only, capital F, whose whose curl is 0. Consider its curl is 0. Now, if its curl is 0 and I have the vector field is such that its curl is 0, df2 by dx minus df1 by dy k vector. Understandable, right? In 3D, now place everything. d d df df3 by dy minus df2 df2 by dz in I direction, like that in z direction, in k direction. You take a curl of f. F is such a Cartesian coordinate equation. The curl of f is 0. F I have taken is there are available f in some magnetic field, some electromagnetic field, where its curl is 0. If that is the case, now then what is the line integral of a circle? What is, if curl is 0, then what is line integral of the circle? Okay, one question. If I know line integral of the circle, then what would be the line integral of an ellipse in that vector field? That is the question. If I know line integral of a circle, then what is line integral of a ellipse? That is under question mark. Okay. Now curl of f is 0. Okay. If curl of f there it is 0, then what is the line integral? What is the line integral for a circle, and what is line integral of an ellipse? Calculating line integral of ellipse is not easy. Ellipse, for ellipse, I believe that integration is not easy. So what is the, if I have capital F, if I have capital F dot dr vector, capital F, whatever the capital F I have, I'll bring it. I don't remember it. So if I have capital F dot dr vector for a circle, if I calculate, then for that capital F, what is the line integration for an ellipse? Okay, x square by a square plus y square by b square equal to 1. Circle is x square by a square plus y square by a square equal to 1. That is the circle. If I have a vector field for which curl is 0, for which the curl is 0, then if I know the line integration of a circle, I'll bring it. Then what is the line integration of the ellipse in that vector field? So what we can do is we can take a circle. This is famous example. This is no this circulation is a circle, and on top side of this I take an ellipse. Bottom side of it, the circulation is a circle, and top side is ellipse. Now this is the surface. Now Mr. Stokes is saying if I have a surface, then curl there is a vector field, then curl of the vector field dot dA vector integration over the surface is nothing but the circulation of the circulation of the curve around it. But this surface has two curves. Bottom curve is circle and top curve is ellipse. I can draw an ellipse, I can draw a circle and then make a surface around it. Now curl of f is 0. Curl of f is 0. So curl of f dot dA vector integration along surface is 0 equal to the line integral, the circulation, we use term circulation or line integral along the its end curve around its peripheral. Now there are two peripherals, but both will be in opposite direction, not in the same direction, because surface is same, and it is supposed to be same boundary, but boundary got dissociated in two regions. They are not two different boundaries. There is same boundary, one boundary only. There is one boundary only, but somehow the surface become like this, so that there is two boundary came into the picture. So that direction will be opposite to each other. So one line integral is capital F dot dr vector. Another line integral will be minus F dot dr vector, because direction is opposite, equal to 0. That this proves that F dot dr1 vector, because one r1 is circle and another is dr2 vector, they are equal to each other. Stokes is saying that line integral of a curve, line integral of a circulation means closed curve, is nothing but whatever surface it is making, surface integration of curl of that vector field dot dA vector. Curl of vector field, I have said it is 0. Then right hand side 0, left side line integration around the perimeter of the closed region. So that there are two parameters, one parameter this side, another parameter this side. They are in opposite direction. So one is for closed loop 1, one is closed loop 2. I have to add it as per the Stokes, because two closed regions are coming. So one is C circulation. For C1 circulation, capital F dot dr vector, I can say R1 vector because one is circle, plus circulation of capital F dot dr2 vector. Okay, where the circulation is in opposite direction. So it will be, if one is A to A, then another is also A to A with opposite direction. So in between plus is there, that will change into minus. Now they are in same direction. Now when they are in same direction, now minus equal to right hand side 0. So they are equal to each other. So in a vector field where curl of f is 0, then as per the Stokes, if I take any surface and it has two circulation, two boundaries, then their line integral will be 0. So in that case, the line integral of the ellipse will be same as line integration of the circle. We will proceed and probably we will have one session only. That we will see curl vector field. I know vector field, and if it is path independent, then it is gradient vector of any algebraic function, potential function. What about if I have a vector field? Then what about curl vector field? Curl vector field. Gradient vector we have learned, and that is path independent. What is curl vector field? So those things we will try to bind up in one session. So that we will see.